And so my task was actually to review analytic approaches and the connection between perturbation theory and the halo model and so on. And I thought I will actually start with the dark matter, just to set the stage. I know this is a workshop on the biasing, but I want to set up the stage and just to see what the issues are in the modeling, perturbation theory modeling of the dark matter, and then we can move on to the halos and galaxies. All right, so first of all, quickly, perturbation theory, we do two different types of perturbation theory. It's called Eulerian or standard perturbation theory, or Lagrangian perturbation theory. And but we also know that perturbation theory cannot possibly give us the correct answers. And the reason has been clearly shown, for example, in this paper, 1D example where you can, where perturbation theory, in fact, just the Dodge approximation is exact up to the shell crossings. And you can see, for example, this is not really working that well. Yeah. So, for example, the full nonlinear solution and the Zdovich are right on top of each other after the shell crossing, and then after the shell crossing, they start to differ. All right, so that means we cannot, with perturbation theory, go all the way. In fact, the similar thing happens in the 3D, but in 3D it's actually much more complicated. I'll get to that. But here's, for example, the Zdovich approximation, or 2LPT against the full simulation. And again, you see that at the places of shell crossings where the halos form, that's where things go wrong. You can do the simplest possible thing, which is that you can just take the ratio of the true answer divided by the perturbation theory answer and parameterize basically your ignorance, or the stuff that you cannot do with perturbation theory. And you can do maybe some simple expansions into even powers of k. And that's the so-called EFT approach, at least in the simplest possible version of it. All right? And so, for example, in 1D, you can do this. And you can see that if you add one more free parameter in this case, from this k-square coefficient, that takes you to higher k, and then if you add 2 or 3 more, then it takes you to even higher k. So it's just basically parameterizing your ignorance by doing this. All right, so in 3D, it's actually more complicated in the sense that we don't even have an exact perturbation theory solution. And so we actually don't know in 3D how to do perturbation theory. That's why there are so many different approaches: standard perturbation theory, Lagrangian perturbation theory. And all of them have issues. And the issues have to do basically mostly with small scale fluctuations producing higher and higher velocity dispersions or displacement dispersions that then show up as a spurious signal, which is not there because of these shell crossings. All right, so this is just a plot showing this spurious signal here. I won't go into the details, but I just want to say quickly that there are different approaches, different ways of parameterizing this ignorance that I mentioned before, and some of them work better, some of them work worse. In recent papers shown here, it has been shown, for example, the 2-loop SPT plus an extra 1 or maybe more free parameters is currently the best model on the market. But even there, if you just assume that this number is constant, it can only takes you up to k of 0.2. And if you add more free parameters, then maybe you can go to 0.3 or so. So the basic message here is that with perturbation theory, it's really, really hard to go to much higher k than nonlinear scale of order, wherever nonlinear scale is at redshift 0, it's 0.2. So in order, therefore, to go, let me skip this. In order to go, so this is basically the statement I made here. I don't think I have anything else here. So this is the statement I just made, right? That basically with this EFT approaches, you can go to k of 0.2, maybe 0.3 or so. So for higher k, then what we usually do is we try to do this with a halo model. And a halo model is we drop down spheres, right? And then we try to model the radial distribution inside the spheres with a 1 halo term, and we add that to the 2 halo term. One simple way of doing this is to say that, let's say the 2 halo term is the simplest possible perturbation theory, maybe it's a Zdovich model, and then you add 1 halo term on that. And you can, in fact, expand the 1 halo term into various expansions, like even powers of k, or maybe Pade expansion, and build up the model this way. Here I'm just showing, for example, the difference between the full model minus this Zdovich. And you can see that the difference looks sort of like a 1 halo term, except it has to be compensated low k. This is the regime where these EFT terms do a better job. This would be these kind of lines. But then, as I said, these terms break down here, because they overpredict the power. And on the other hand, if you do some simple parameterization of the halo model, then you get something like this. And you can build up the model this way. So it still has free parameters, obviously. All right, so, okay, here's another example of basically how we do this. You know, there's a low-edge approximation. Doesn't have enough power in small scales, as we said, but then we start adding these halo model terms, which we can expand into these powers of k, you know, k to the 0, k squared, k to the 4, and that's how we build up the model. Yes, f of k is this compensation thing here. So the halo model in the simplest version goes as k to the 0 at low k. We know that has to be wrong for the dark matter because we have mass and momentum conservation, and so you have to put in something. This f of k here is just some simple fitting function, but you know the more correct approach would be actually, as I said, to use EFT parameterization at low k, which is shown here. And you can see the blue line is this very simple version of this f of k, and this is the more correct version using EFT.
So this f of k doesn't go to 1 without change, it goes up.
Who's?
F of k.
F of k here goes to 1. Yeah, I didn't write it. It's just 1 over 1 plus k squared.
So you're not using that part to describe the actual 1 halo.
I am, and but it's really coming at 2. This is really effectively a 2 halo term. I'm just sweeping all of the halo terms into this one single term that I'm multiplying one halo term with. That's this f of k. And, you know, it's 1 here, f of k, and then this should be 1 here, and then it's going down. Okay, so another discussion. So we'll use this for modeling galaxies as well later. But before I get to that, let me just discuss one more topic in the context of a covariance matrix of dark matter. So let me start with the dark matter, and then again we can talk about galaxies later. Whenever we talk about covariance matrices, there's always 2 terms to the covariance matrix. One is the so-called disconnected part, which is just the Gaussian part, and which is just proportional to the product of the power spectrum. Suppose we want to know the covariance matrix of the power spectrum, and this will be the disconnected part, the Gaussian part. And on top of that, there's something which is connected part. Now, it turns out that the connected part, in a very simple way, can be modeled just as a number times the product of the power spectrum. I'll show this in a second, but this is basically a smooth response to the long wavelength modes. All right, some of these long wavelength modes come from the outside the survey box. We call this supersample variance. Some of them come from the inside the survey box, and it's not supersample variance, but it still has a very similar response. So we try to look at this using perturbation theory. As I've just mentioned, the leading term is this supersample response. If you have some long wavelength mode, which just doesn't average to 0 across your survey, then this will basically just shift up and down the power. In fact, it will do slightly more than that. It will shift up and down the power. It will also modulate by taking the derivative of the power spectrum. And essentially, the effect is like changing the curvature. Change the curvature changes the amplitude, but it also changes the scale. And change of scale is this effect, and this is a change in the amplitude. No, they're all important. You mean this term? No, I mean they're for BAO actually. It's well, I guess the question is this term important for BAO measurements? And the answer is probably not because of the 1/3. Yes. All right. So this is just the supersample variance. Then beyond that, there are also contributions to the covariance matrix from modes inside the survey. All right, the modes that actually average to 0 on the survey. And for that, one can use the perturbation theory. And there are 3-level calculations that one can do that have been done actually back in '99 by Skochimara et al. And it turns out that this term actually doesn't do very much. On top of that, we can start adding so we have extended this to the 1-loop calculation, where one can think of it in a very similar way. One can think of it as a response to the long wavelength modes. And it turns out this response is also similar to the response to the modes outside the horizon. It's, again, some power spectrum, again, some derivatives, and second derivative. And so one can write then the covariance matrix divided by the power spectrum as, now this time, this is a quadratic term. That's why this is 1 loop. It's an integral over the p square. This is just a sample variance of the long wavelength modes. Okay, and there's actually 2 here, right? That's why it's 2 divided by 2 pi squared. You get 1 over pi squared. And then this is the response to the long wavelength mode power. Okay, so and just one more step. So something we are just looking at now is we have also added the 2-loop calculation to this. And this is this analytic formula that I've written down on the previous page. The green lines are the one loop calculation, the exact one loop calculation, and the red points are the two loop calculation. And you can see that two loop basically enhances the power here. This is actually I just got this today. We are running the simulations now where you add small amount of power, and you ask what's the response to this, and this is the response, and this is the one loop calculation. And you can see that this actually looks very similar to the two loop here, but we haven't yet put the two together. So and finally, I just want to mention that adding the EFT terms to this kind of calculation actually doesn't seem to improve. In fact, it makes things worse. And I'm not sure I understand that very well, but it doesn't seem like EFT can work for this kind of problem. All right, so the final result of this calculation when you do two loop is actually a 12th order in density, right? A 6th order in power. So I'm very impressed that we have the highest power perturbation theory calculation. But it's only very restricted, of course, right? We're really looking at a very restricted number of terms here. But how well does it compare to the simulations? Here I'm showing the covariance matrix. Well, why is it enough? Yeah. I don't know. I mean, well, I mean, the two loop SPT really, that was the argument before, really does help a lot compared to the one loop SPT. And since so two loop is really 3 orders, right? But since we're looking at covariance matrix, that's why it's 6 orders in power, right? Which means 12 orders in density. Right? It's a very restricted version of the tri-spectrum, which is the covariance matrix. I don't think this would. Yeah, it's very very specific limit. Yes. What's that? Yes. So I didn't go into details, but this here is this expression here. All right. This is the long. This is the response of the one loop power spectrum to the very long Weyland mode. So you add some amount of power to the long Weyland mode, and you ask how much does what's the response to that at one loop level. This is the answer. It's proportional to the power. Right? So you see this is one loop because this is one power. There's another term power. Right? So it's p squared. That's one loop. So that's this line here. That's the analytic one. The green dots are just more correct evaluation of the one loop. So they do agree very well, at least here. And then the red is a two loop calculation. So we added now another power of p to that. It's a two loop integral in this case, and that enhances the power here. Yeah, at high k it is. Yeah. And this is again the blue is just this, except that here I've also had this EFT term, this k square alpha square, which seems to suppresses power and doesn't seem to go in the right direction compared to this, right? And this is and these are now simulations here. So the correct thing to do is to compare basic simulations to the two loop, and it seems like it's a reasonable agreement, but we haven't really done it. Here, this is the derivative, numerical derivative, and so here we have actually the feature we have added is actually here. So things do go crazy there because this is where we added a bump basically here. Yeah, the y-axis is the derivative. So other place where you have the feature, things do go crazy. Okay, so how does it compare then to the simulations? So these are simulations from Blott et al. They ran 12,000 simulations or something like that, some crazy number like that. And they've computed the covariance matrix. And so here are the different contributions. This is the 3-level, the supersample variance contribution is this one. Then the 3-level is this one. Then the one loop level is this, and this is the total. Okay, and here I'm actually also including the covariance, the Gaussian part here. So this is for k of 0.1. This is for k of 0.3. Okay, the Gaussian part is actually very small now because so it's all really in the correlations between the modes. No. This is just one loop. Yeah, that's because we have added something to the one loop here. Yeah. So we have added some nonlinear response already here to the one loop, which was fudged in these plots, but now we think we have actually formal derivation. All right, and this is where we put all these modes together, right? So, the bottom line is, maybe perturbation theory is good for something, right? Which is covariance matrix. But what are the implications of this covariance matrix? Let's look at that which I think is more interesting. It's all really the response of different modes to the same long wavelength mode, right? So the way to think about this, and then you just add up these long wavelength modes, and if they all respond the same way, then you can just treat everything with a single response. And that's what is shown here. We now diagonalize this covariance matrix, and we find that it's basically just one large eigenvalue, and the rest is 0. We have diagonalized covariance matrix minus the Gaussian part, minus the disconnected part. So the way to think about it is that the full covariance, the full connected covariance matrix is just a single eigenvalue times eigenvector product with itself. Okay, and this eigenvector is here as a function of k. So this is the principal component decomposition. This is just looking at the square root of the diagonal matrix. You get the same answer. So this means that we can write the non-Gaussian part of the covariance matrix like this. And this means that when you have a covariance matrix which looks like this, then you can actually write, you can treat it two ways. Either you put it in the covariance matrix, or you think of having another nuisance parameter, external nuisance parameter, which is just a free coefficient times this eigenvector. And you can go and fit the data using this fictitious parameter, and you can marginalize of this fictitious parameter, and that way you have actually accounted for all of the non-Gaussian covariance matrix effects. Right? Because basically the idea is that the long wavelength mode, what it does is just shifts the power up and down with some structure, and the structure is determined essentially by this eigenvector. Yes, yes. No, the Gaussian part is 2p square always, right? Gaussian part, this one, right? Yeah, just 2p square, right? Times, divide by number of modes.
But this for that matter, right? For galaxies.
Same. Yeah.
For galaxies, didn't you say that
Oh no, but that goes into the p, right? The stuff, whatever noise is, whatever is Gaussian, Poisson, non-Poisson, that goes into the p. This is the true p. This is not a Gaussian p or anything like that. This is the true p. Right. Yeah. So no, in fact, we have looked at this. For galaxies, this is still preliminary work. Nick may show some plots. Basically, we find very similar structure of the covariance matrix. Again, single eigenvalue works pretty well.
the eigenfunction supposedly will scale small.
This.
Yes.
Which is why this perturbation theory maybe is useful, because in that case we actually do get that as well. Yes. Right. This certainly is an important dependence on the redshift of this. Yes, which is its own.
Although even if you didn't have to run simulations, you know what the Gaussian piece is with pure analytic calculation, and now you just need to find one vector as opposed to a full matrix.
Yes, that certainly is a lot easier. Right. I mean, what people are doing right now is very not efficient in the sense that they feed the full covariance matrix, and then they get all sorts of noise issues that are not under control. Well, I just explained. I mean, the reason is that it's a response to the long wavelength modes, and the response, nonlinear response, is always the same.
Independent of changing the power spectrum by cosmology.
This is the response. This is a one-loop response. It's always the same. You see, this response does not depend on k of this guy here, right? In the limit where this k is much smaller than the k we're looking at. Now you're asking, why is that limit relevant? It's because this integral here is the largest in the low k limit. Why is it? Because in the low k limit we have the largest sampling variance, right? At high k, sampling variance is small, right? So it doesn't. You average over so many modes at high k that they don't contribute to the covariance. Uh-huh. Yeah. Mm-hmm. Right. Yeah. Yes. No. Right. Yeah, and in fact, to connect to the Halo model, in fact, the way we wrote down this one here was actually in the concept of the Halo model. The idea was just you have some large clusters, in your sample, whether you have them or not, we'll just move everything up and down, right? in the concept of one halo term, that makes sense. It's less obvious why it makes sense also for the two halo term. And for the two halo term, then that's where perturbation theory calculation is more useful. But they both give you the same answer. Right? Well, and that's what this is. For example, at one loop level, this is the full calculation compared to the low k limit. At two loop level, this is the full calculation. Right? These are the full calculations. But the point is that the low k limit is good because at the low case you have the largest variance of the modes, and right, that's when you integrate over all the modes. It's the low k modes that have the largest fluctuations, and it's the response to those guys at high k that matters most. Okay, anyway, I wanted to talk about galaxies, I guess. So let's talk about galaxies now. How am I doing with time? 20 minutes or more? Yeah. So, what of this can be applied into galaxies? You know, it's the same idea for galaxies, right? What do we want to do is we want to get as far as we can with perturbation theory, but not more than as far as we can, and then beyond that, we have to account for what we cannot handle with perturbation theory. We have to account for with basically modeling our ignorance, okay, while obeying all possible symmetries. So how do we do that? Well, you know, we can add this. We can do perturbation theory, of course, first for the dark matter. Then we can add biasing terms and do perturbation theory of those. And then whatever we haven't yet resolved, then we can try and do with this ignorance, right? For example, we can add a k-square term, just like EFT term, and that will work. But you know, as I argued, it actually doesn't take us far enough in k, because k-square is not a good expansion, and that's why you know very often we do something more than that by using the halo model. But really, I want to emphasize that the halo model and the EFT k-square term are really the same thing at low k limit, right? So, okay, so how does that work? Here are plots of redshift space distortions, and these are for different halo masses and for different mu terms. I won't go into details. Nick will give a talk about this, but the basic idea is, well, you know, you try as much as you can to model the halos using this nonlinear bias parameters, B2, BS square, and so on. Okay, and one thing that is always clear when you model redshift space distortions is the linear theory. Linear theory will be flat. Linear theory never works. Okay, so you really have to do something about nonlinear effects. Okay, so when you model this in, and so okay, this is what is the level of halos, but then you have to go beyond the level of the halos. You have to start adding satellites, right? Which means you have to add one halo term, and the question is, do you need to add the structure to the one halo term? This is answered here. For example, we're looking at the one halo term. What have we done here? We have taken the typical HOD model with satellites, and then we replaced the satellites, put them at the center of the halo, and took the difference. The difference is the structure of the one halo term, right? The k-dependent structure. Because we know that otherwise one halo term we can model it just as a k to the 0, you know, just change in kind of shot noise. But if there's some k-dependent structure, then you have to account for the difference. And this is shown here, and you can basically show that this is a negligible effect up to the k that where we usually want to go to, which is 0.5 at most. So it's orders of magnitude less than 2 orders of magnitude less than what we care about. And so we can basically assume that the one halo term, in the power spectrum at least, in the real space power spectrum, is just a constant shot noise term. All right, so that's, but if you want to model beyond that, you can add a term like this, and that would also work. Okay, so in real space, satellites don't do much except for adding for the shot noise. Of course, when you go to redshift space, then things are much more problematic, and this is shown here, which is what happens to now the same question when you start changing, when you start looking along the line of sight. Mu equals 0 is transverse to line of sight. This is the real space power spectrum, and high mu is along the line of sight. And what we're finding are these, in pretty large, what we call fingers of God effects, right, due to the satellites. And you can see, for example, that even at k(2), in the radial direction, you get almost 50% suppression in power because these fingers of God are so large. So again, here you could do, even powers of k expansion, 1 minus k square, but that would not be a very good expansion. So that's why we typically go to these more fancy resummation terms. And for example, we either do exponential or Lorentzian or something like that. And these are shown here as one is Lorentzian, one, well, actually, they're different. They have different values of velocity dispersion. But the basic idea is you want to go beyond just a k-square expansion, so like a Gaussian or Lorentzian. Okay, so this is, and the other thing that is important is that these fingers of God are important both for the 2 halo terms and for the 1 halo term. So you want to add them to both. All right, so Nick, I guess we'll go more into details, but I just want to now, take a step back and ask, what are the remaining challenges right now for this modeling of galaxy clustering in redshift space? It's same as for dark matter. Perturbation theory alone doesn't take you high enough in K. Here is an example of cross correlation between halos and mass. Here is perturbation theory model based on one loop biasing model. One loop means we add B2. So we expand the biasing in terms of B1 delta plus B2 delta square and so on. There is a tidal tensor term, BS square, and there's a third order non-local bias, B3 non-local as we call it. All of these contribute at one loop level. And here is basically how well this works compared to simulations. It can take you maybe to up to K of 0.1 or 0.2, but then not beyond that typically. So that's very similar to how far the dark matter one loop perturbation theory takes you. Except, of course, here now we have several parameters that we have to introduce, right? Several of these biasing parameters. So you can either go to the 2-loop level and introduce a whole bunch more parameters, or maybe you can try and change the expansion basis. And rather than work with this perturbative expansion, you try and do the halo modeling. So here's the simplest possible thing one can do, which is, again, similar to what we did for dark matter. So you just say, okay, assume your halo matter cross correlation is just given by B1 times the Zeldoid for the matter, and then some simple one halo model, and you get a decent fit with about the same number of parameters, which can extend to a much higher K. So basically, it's just a different basis, the halo model, but it can be a useful basis. You still need to, of course, fit these parameters to be a function of mass and redshift. This is a Pade ansatz, which what is nice about this is that it goes to 0 at high K. Right? That's the problem with the Taylor expansion. Right?
This is a bunch of free parameters that you can do in any given simulation. So what do I gain by this? Where would I want to use this? If I want to use this as a cosmology, I don't want to have something where I don't know what the parameters are.
No, well, the idea is that it is only a function of mass, halo mass, essentially, and maybe redshift, but So. No, well, it's not. Well, this is where redshift enters. Yes, sigma 8 is the only parameter that matters, which is the same as redshift. But anyway, so if you Fourier transform this thing, by the way, you get this kind of thing. So you do see these inflection points, which you would not actually see if you just do this stuff. So it has some nice features that it also works well for the correlation function. This is this inflection point that we talked about earlier, right? This is the 1 halo term, the 2 halo term, and there's some kind of transition where things go down and back up. Okay, so the second challenge. So this was the cross correlation between halos and dark matter. Second challenge is the what we call stochasticity. Right? So you can take the difference. You can basically whatever is not in the cross correlation, there's still something left in the autocorrelation. So we can take basically autocorrelation minus whatever is in the cross correlation, and call this stochasticity. The reason to define it this way is that so that this, nominally, this thing doesn't depend on the p-linear on the large scale. It's really just stochastic term. In the simplest models, of course, it's just 1 over n bar, the shot noise term. But for halos, we find, for example, here's just one example. It's never that, even at low k. In this case, I've chosen a fairly large halo mass bin. It's negative. That's due to the exclusion of the halos. But what is more troublesome, of course, is that it has a significant k dependence. So Tobias has talked about this, how we can model this using bias expansions. And he's shown, for example, that it has B2 and B3 and B4 and so on. They all contribute on top of this exclusion effect. But this is something that we still need to understand better, basically. Stochasticity is a big problem. Now, how much does it matter? Unfortunately, I don't have a plot here, but typically these kind of effects are of order 1 or 2%. So they're not big, right? And we think we can understand them, but this is certainly something where we need to do more work. Okay, Nick, I think we'll talk about this. This is when you put everything together, we get good fits, right? But these are models where, so we go to k of 0.4. These are models where we now have divide everything into satellites and centrals, and we don't assume that there's any connection between satellites and centrals. We don't assume that the centrals, there has to be a satellite where there's a central, and so on and so forth, right? So this is all the free parameters that goes into this modeling. But that's, at the end, we get good results. As I said, Nick will talk more about this. So let me spend last few minutes just talking about what we spent the whole day so far, which is, is there a second parameter in the biasing besides the halo mass? We talked about this assembly bias. Now, in a way, we know the assembly bias is there. We've known it for decades. The way to think about this is, as Andre was arguing, we usually define halos with over density of 200 or linking length of 0.2, but we don't have to do that way. There's no justification for that, really. Suppose you do that with an over density of 1,000 or link length of 0.1 or something like that. Then what will your halo finder find? You will find a whole bunch of halos now, but they would really be some of them will really be what we call subhalos inside the larger halo. Right? So if you then split those halos according to their environment, the ones that don't have a close halo will have bias will have low bias. The ones that do have a close halo are really satellites inside a larger halo and will have a lot larger bias. Right? This is something we have known for a long time, right? So if this is all there is, well, we have known it. Of course, the only reason why we talk about this is because we think that over density of 200 or linking length of 0.2 is somehow special. But it's not special, right? So you can, again, think of the halos defined with linking length of 0.2 as being, close to each other, in which case they're part of some larger halo, and they'll have large bias, or they will be, if they are away from each other, then they will have lower halo bias. So we tried this just for fun. So we have taken halos of the same mass, 13.5 to 14 in log m. We measure cross correlation between halos and mass. And at high k, they all give the same signal, which means they're living in the halos of the same mass. But now we split them according to the proximity to another halo of the mass greater than 10 to the 14. And we find that at 14 megaparsecs is where we get half. Half of them are closer, and half of them are more distant than 10 to the 14. And in that case, if you don't split by that, then this is the curve, the cross-section curve, flat bias of around 1.5, and then one halo term. But if we split it that way, then the points that are far from nearby clusters really are going to have bias, which is 0.5. In fact, if we did this split at 30 megaparsecs, this probably would go negative. Right? This would be voids really. On the other hand, the ones that are closer, 14 megaparsecs or closer to these guys, they pick up just the bias of the big guys, right? And they get the bias of the 10 to 14. Right? This is the sample of the clusters halos larger than 10 to 14. and these guys pick up pretty much their bias. Right? So now you can see there's a strong scale dependence here, right? Starting roughly at 10 megaparsec and down, right? On our case, roughly 10. Whereas there isn't any here. So it is this scale dependence that we need to worry about, right? Because this is, in our models, if we want to go to small scales, there's a lot of information. But if we have these kind of problems, then we need to understand this better. So the scale dependence is a potential issue. I'm not so much worried about the fact that large scale bias. So information up to here, up to 0.1, we'll still get the same correct cosmology if we use information only up to here. It's only if we go to higher k that we need to start worrying about these issues.
So is that scale being set by the mass scale of the approximate neighbor?
This one?
Yeah.
Well, yeah, I guess it's 14 megaparsecs, yes.
I mean, it's whatever the largest scale is that you set some constraint on the density. It happens to be 14. Yeah, that's the scale. Because after that, it's flat.
Yeah. So we've done one more way of doing this. Now this time we're not looking at the closest greater than the 14, we're just looking at the closer than 10 to the 13.5 and larger. In one case versus this 10 to 14, but we're going only up to 4 megaparsecs in this case, which means in some way we're looking at even more extreme cases because we're requiring that there has to be another halo closer to 10 to the 14. Sorry, closer than 4 megaparsecs, either above 10 to the 14 in this case or above 10 to 13.5. And this is if we don't do any cuts. Okay, I just want to quickly explain what I'm plotting here. So the dashed are all cross correlations with mass. And again, at high k, they just give you the halo mass. So that's why all three lines, green, blue, and red, they all converge to the same because the mass sample is the same in this case. But they're split, again, by their environment. Here, there is no split. Here, you require that there's another galaxy close within 4 megaparsecs, and the bias goes up. And if you require there's another galaxy, another halo closer than 4 megaparsecs, but that halo has a mass greater than 10 to the 14, then the bias goes even further up. Right? Yeah, but it's still useful to know whether it's environmental bias or assembly bias. Which one is the primary parameter, right? I think that's useful to know. Fine if that's what you mean, but the difference is that if it's environment, then we think we have a handle. I'm going to get to that, right? Great. I mean, great. I mean, I have no problem with that. But the point I'm trying to make here is, if it's just the local density that determines all of this, then we have handles then we know how to handle it, because then we can look at the 2 and 3 point function statistics. Okay, that's going to be on my next slide. Right? Well, that's right. I didn't say dark matter density here. You can think of this as being a 3 point function, right? I'm splitting based on the third point, right? I'm doing a two point correlation on the basis of where the third point is. That's a 3 point function, right? And it's a 3 point function defined in terms of the tracers, right? Galaxies or whatever. Right.
I split on internal property like concentration or the mass. I get a qualitatively different scale bump if I split on the internal structure properties.
Sure. But right. So
you could not encompass that effect, depending on what scale.
Well, I don't know. I mean, look. I mean, as I change this distance, the scale dependence also changes, right? I mean, so the question is then, what is the appropriate environmental scale that you should be looking at? But again, that can also be encompassed in terms of 3 point function, right? Because I can do this as a function of the third separation, and scanning that. So I have a lot of information I can do. If everything is encoded basically in this, 2 and 3 point functions, then there's there's a way to handle this, right? That's all I'm trying to say here. Now, of course, there's another effect that is most clearly seen here, which is this stochasticity effect. As we go, so again, remember, this is a cross correlation, this is autocorrelation. The difference between these two is the stochasticity. And you can see this stochasticity is huge when I define it, when I require the two are closer than 4 megaparsecs away from the 10 to the 14 meg. And even in the other case, even in this case, as the bias has gone up because of the environment, the stochasticity has also gone up. Right? And that's basically, again, it's just a one halo term of the satellites, right? We know that if we have satellites, yes, they will have larger bias because the satellites inside the larger halos, but there will also be a larger one halo term because they are close pairs. Right? This is exactly the same effect, except now applied to larger larger overdensities, right? So you can think of one way to think about this. We should really be talking about even larger halos than defined with overdensity of 200, maybe overdensity of 10, right, on a few megaparsecs. And we are really talking about sub-halos in these larger overdensities as being halos as we talk about them today. Right? But basically, if everything is encoded in terms of the local overdensity, in terms of this 3-point function, then there is a way to identify these effects and go and look for them in the data, right? If it has something to do with environmental density.
But on halo level, we know from simulation, actually it's the tidal field, local tidal field, that is the driving, well, maybe not the driving, but at least it's more fundamental than the overdensity. Basically, you could do, I select the same overdensity but different tidal strengths, and you look at the, or the other way around. You always see that it is the tidal field that.
Yeah, I don't think that works out that simply into the statistics, right? Because tidal field is not a scalar, and if you look at the 2-point functions, you have to really express something into a scalar. And a tidal field, the only scalar you can build out of the tidal field is actually tidal field squared, and that's a second order effect. Okay, so it's not that simple to translate this kind of studies into the statistics. Okay. So anyway, so that's these are my conclusions. I think perturbation theory can be useful, but it has its limitations. Shell crossing being the obvious one, but really in 3D it's much more than shell crossings. It's really, perturbation theory is bad in some sense, and we need to understand how bad it is, and we need to control it. Nevertheless, for things like covariance matrix, seems to work well. And then we apply this concept to the halos. We really need to remember that there are some terms that are non-perturbative, and fingers of God are the most obvious thing. But this halo stochasticity is also non-perturbative, and again, something that we really need to worry about. And things like that, and environmental bias needs to be studied more.